Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be talking about the topic of non-dimensionalization and scaling arguments. Non-dimensionalization and scaling arguments. So dimensionalization transforms a problem into dimensionless form, and we use approximate methods to reduce difficult problems using comparison of terms. So the idea is to use approximation methods to reduce difficult problems based on comparison of terms. Right? And the problems of interest, the problems where variables of interest could be large or small, slow or fast, are compared to the other terms. Right? So that will bring us to the topic of scaling. So when we compare large versus small terms, or we compare fast versus slow terms, we are talking about we are introducing the concept of so-called scaling. Okay, so let us see this idea using an example. So the example that we have is again the projectile motion. So case 1, projectile motion. So we consider the projectile equation, xtt is equal to minus gr square by r plus x whole square, and we have t is positive, x of 0 is 0, and the other condition is xt at 0 is v0. So now the first step in non-dimensionalization scaling is we are going to introduce certain characteristic variables through which we non-dimensionalize. So we use a change of variables, t is equal to tc times tau and x is equal to xc times u, where we are going to find these tc and xc, the characteristic variables, later on. So then we have the derivatives d dt will have, using chain rule, will be d tau dt times d tau, and this is going to be 1 over tc times dd tau. Right? And similarly the second derivative will be equal to 1 over tc square dd tau square. And similarly, so now what we have is, let me call this model as model 1. So 1, now using this change of variables, so 1 can now be written as that this is 1 over tc square, second derivative with respect to tau of xc of u is equal to minus gr square by r plus xc of u square. Right? So now we are now in the non-dimensional ODE, non-dimensional ordinary differential equation, where we have non-dimensionalized with some characteristic variables. So the second step of the method is that we are going to collect all the dimensionless groups. So collect parameters into dimensionless groups. Connect parameters into dimensionless groups. So this question here that we had to answer is, how are we going to collect it? So should we factor RHS as R times 1 plus XCU of R, or XC times R over XC plus U? Right? So the solution is that we will with this first choice we can bring out R and we can cancel this R with the numerator. That is, notice that we have an R square in the numerator, and R square, when it is brought out in the denominator, they get cancelled. So that is going to simplify. So with first choice we can cancel R in the numerator. And now my equation, the model 1, is represented as follows. So pi 1 d2u d tau 2 is equal to minus 1 by 1 plus pi 2 of u whole square, with u of 0 is 0 and u tau of 0 is pi 3, where my dimensionless groups pi 1 comes out to be xc by gtc square. Pi 2, dimensionless group pi 2 is xc over r, and pi 3 comes out to be tc by v naught by xc. Right? So we see that these parameters pi i's, they are dimensionless, and they are independent. They are independent in the sense that one cannot be represented as a linear combination of the other two. And finally, these only contains the parameters xc and tc, the pi i's. So this question now that we have to ask, another question we have to ask is, what values should we take for these critical or this characteristic time scale and length scale, xc and tc? So what values of xc and tc to take? Right? So what we have is, so the answer to this question lies in the fact we are going to pick. So we are going to define some thumb rules. So thumb rule 1 is that the pi's appearing in initial and boundary conditions will be set to 1. So pi's appearing in initial and boundary conditions are set equal to 1. So we set the only pi appearing in the initial condition is pi 3. So here in this problem we set pi 3 equal to 1, and we get one relation that xc is equal to tc times v naught. Okay, xc is tc times v naught. Okay, so then what we have is xc. So then what we have is that then the next rule of thumb is that we are going to pick pi's. We will pick pi's and set equal to 1, which is appearing in the reduced problem. Appearing in the reduced problem. So So what is the reduced? So first we have to understand what is the reduced problem. The reduced problem is when we have when we have pi2 set equal to 0, right? So the reduced problem is when we have pi2 set equal to 0 in this case. And now in this reduced problem, whatever pi remains, for example, here in this case pi1, we set pi1 equal to 0. Sorry, pi1 equal to 1. So in the reduced problem, we set pi1 equal to 1, right? And we have that xc is equal to v naught square by g and tc is equal to v naught by g. So this is found by setting pi1 equal to 1 and pi3 equal to 1, right? And now so we have found the critical values of the x and t, and now from here we come back to the original problem where pi2 was not 0, right? So the original problem now is d2u by dt tau is equal to minus 1 over 1 plus epsilon u whole square, with u at 0 is 0 and d2u d tau at 0, t equal to 0 is also 1, right? Here my dimensionless group epsilon is v naught square by gr. Originally it was pi2, but pi2 was xc over r, so we have just plugged in the value of xc. So xc is v naught square by g, so this is pi2, right? So here we may assume that this is this is a very small parameter, because the original problem from where this new problem is derived is the reduced problem where pi2 was set equal to 0. So we may very well assume that pi2 is a small parameter. Okay, so then certainly this method is not unique. We could have chosen other dimensionless groups as 0, and we would have arrived at a different form of the problem. So let us see. So what I am just saying is we have another scaling. We have another scaling in the form that this will lead to different choices of xc and tc, right? So if we have pi2 and pi3 set equal to 1, so in this case the scaled problem epsilon d2u d tau 2 is equal to negative 1 by 1 plus u whole square, right? Here we have u of 0 is 0 and du d tau at 0 is 1, right? And now this problem is a little problematic because we have, of course, epsilon is a small parameter, because when we take epsilon limit, in the limit epsilon tending to 1, we are going to get the model will be 0 is equal to something which is negative 1 by 1 plus u square, and of course at t equal to 0, u of 0 is 0, so we get 0 is equal to minus 1, which is a contradiction. So what we see is that this sort of a differential equation needs another form of treatment, or the so-called the singular perturbation treatment, which we will see over the subsequent module as to how to solve such problems, right? So this is the singular limit. This is the singular limit, and we need to handle differently, as we shall see in few modules down the line. Okay, so then let us for the time being digress our attention to another form of this 1D diffusion model, namely weakly nonlinear diffusion. So weakly nonlinear diffusion. Okay. So suppose the concentration C satisfies the diffusion reaction equation, which is as follows. D times Cxx is equal to Ct minus lambda times gamma minus C times C, where we have the boundary condition given by C at x equal to 0 is C at x equal to L. This is 0, and my initial condition is C at t equal to 0. My initial condition is given by C naught sine of 5 pi x over L. Right? And then notice that the nonlinear term is this C square term, which is the quadratic term. We can assume that the nonlinearity is weak. So assume weak nonlinearity, and which means that the lambda C square term is small. The lambda C square term is small with respect to other terms. Okay, so then we can start the solution to the problem using the standard dimensional analysis and see what similarity variables we get. So let us start with standard dimensional analysis. So dimensional analysis, we see that the dimension of C in this case is 1 over L cube. The concentration, the dimension of the diffusivity D is L square by T, and the dimension of gamma is the dimension of C, and the dimension of lambda is L cube by T, and similarly the dimension of lambda gamma minus C is dC by dt, right? And of course the dimension of the initial condition C naught, it's just concentration, will have to have the same as the dimension of C. So then we can start to introduce characteristic variables. So this is step 1 of the solution method. Introduce change of variables. So we have x is equal to xcy, t is equal to tc tau, and c is equal to cc u. And we see that if we use our chain rule, plug all these new variables, we see, so using chain rule for differentiation and collecting all dimensionless groups, we have that dtc by xc square partial u partial y square is equal to partial u partial tau minus lambda tc cc times gamma by cc minus u times u, right? And what we have is that the boundary conditions are u at y equal to 0 is u at y equal to L is 0, y equal to L, y equal to L over xc. So y is the non-dimensional variable here. So those are my boundary conditions. Okay, so then from here we can figure out the dimensionless group. One is this one, the other one is this one, and the third one is this one. So my dimensionless groups pi 1 is dtc by xc square, pi 2 is lambda tc by cc times cc, and pi 3 is gamma by Cc. And then we could have two more dimensionless groups corresponding to the initial conditions. Pi 4 is L over Xc and pi 5 is C naught over Cc. And of course, the thumb rule 2 says that we set pi 4 and pi 5 to be equal to 1. So set pi 4 equal to pi 5 equal to 1, and from here we can find that Xc, the characteristic length, is L and the characteristic concentration is C naught. And then, so this is thumb rule 1. So then thumb rule 2, the thumb rule 2 says that we are going to set, in the reduced problem, we are going to set the remaining dimensionless groups to be 1. So first in the reduced problem, so we have to see what is my reduced problem. So the reduced problem will be when we don't have any nonlinear term. So we set this characteristic group pi 2 equal to 0 to bring us to the reduced problem. And now the only dimensionless group that remains is pi 1. So we set pi 1 equal to 1. So the only group remaining in the reduced problem is pi 1. We set it equal to 1. And from all these conditions, we see that my time scale comes out to be L square over D. Right? And now the resulting differential equations in terms of the remaining dimensionless groups will be partial u partial y square is equal to partial u partial tau minus epsilon b minus u times u. Right? So epsilon is the only group remains, that is pi 2, and we have that, of course, the initial condition for this model, the initial condition or the boundary condition for this model comes out to be u at 0 comma tau is equal to u at 1 comma tau is equal to 0, and the initial condition is u at y comma 0 is sine of 5 pi y. Right? And then my dimensionless parameter epsilon turns out to be, epsilon is lambda C naught L square by D, and B is coming out to be gamma by C naught. And in this case, we are talking about weak nonlinearity. So we must have that epsilon is much less than 1. Of course, as we have seen in the previous example, that this sort of a scaling is not unique. We could have more than one option. We could look at another option. The second, so another scaling option as follows. Another scaling option. We could have set pi 1, which is dTc by xc square, to be small. Right? So this is our epsilon. And then we in the reduced problem, we have pi 1 is set equal to 0, and now in the reduced problem pi 2 is 1, and so my time scale comes out to be 1 over lambda times Cc, or this is also equal to 1 by lambda times C naught. Right? And then my equation reduces to epsilon u y is u tau minus b minus u times u naught, where this time my epsilon comes out to be d by C naught lambda L square, and my b comes out to be gamma by C naught. Right? So b comes out to be gamma by C naught. And again, we have come to a point where this new model is a singularly perturbed problem, where if epsilon goes to 0, we are talking about the singular limit, right? So again, we have to solve this new model in another way, which we will see in few modules from now. Okay, so we have seen that, notice that in this problem we had seen that the resulting ODE in the form of the dimensionless group can be either represented in the form of a regularly perturbed problem where epsilon does not appear with the largest order differential term, or it can be represented in the form of a singularly perturbed problem where epsilon appears as a coefficient in the largest derivative term, right? So which brings us to the point that we must try and solve these types of problems with the so-called perturbation methods. So in the next module, I will digress for few topics, I will digress for few modules and try to look at how to find the solution to these perturbation problems. Thank you so far for listening.